In this video, we're going to do two or a few practice questions preparing for the final exam of the semester, the final lecture exam of the semester. So these are going to cover chapters 18, 19, and 20. So practice question for exam 4. It says, write the symbol for the nuclide that would produce 243 americium upon alpha decay. So this is a really good question because what you have to do with this one is you have to kind of go backwards. So what it's saying is that it would produce this 243 americium. And if you look up americium's atomic number, it's 95. So if we're producing americium by alpha decay, the other particle that we're producing is a alpha particle, which is a 4/2 helium. So if we work backwards, we have to add these two together. So the 95 plus the 2 is going to give us 97. And then we have to add 4 to 243 to get 247. So if you look this up on the periodic table, you get the element Bk, which I think is berkelium. Don't quote me on that. But the process, though, is, and what makes this a more difficult question, is that you have the nucleus as the product and the decay particle, but you have to work back to get the nucleus that you started with. So for the next one, it says, which of the following cations is capable of oxidizing lead to lead 2 plus under standard conditions? So we have to go in the book and look up the standard reduction potential for these things. This is like an activity series question. So if you look up the lead 2 plus redox potential, you get minus 0.13 volts. Okay, and then if you look up the redox potentials for the remainder of these things, we get minus 1.66, we get 0.34, we get minus 2.38, and we get minus 0.76. So these are the standard reduction potentials. So I've looked those up. So this would be aluminum plus 3 electrons. Aluminum 3 plus 3 electrons gives aluminum. Copper 2 plus 2 electrons gives copper. Magnesium 2 plus 2 electrons gives magnesium, and so on and so forth. So now the question is which one of these is going to be capable of oxidizing the lead? So what we're looking for, so the lead 2 plus 2 electrons goes to lead. This has an E naught equal to 0.13 volts. Minus 0.13 volts. So if this is minus 0.13 volts, we know that anything that's higher than this is going to be a stronger oxidizing agent, meaning those are going to be the elements that are going to tend to want to be reduced. So anything with a higher reduction potential that's more positive than this are going to be the ones that are going to be able to oxidize lead. So the only one with a higher standard reduction potential is copper 2 plus. So that's going to be the answer. So if you think about it this way, we can kind of write a cell here. And if you want to kind of review, we have lead 2 plus 2 electrons gives lead. So let's write this for the copper cell. So let's say that we had copper and it's going to be reduced. So copper 2 plus 2 electrons goes to copper metal. So the E for this is equal to 0.34 volts. And lead 2 plus 2 electrons gives lead. And the E for this is minus 0.13 volts. So in order for something to be spontaneous, right, we need to have an E cell, which is going to be a positive number, be equal to the cathode minus the anode. So E cat minus E an. So if we have minus negative 0.13 volts, we need some number over here that's going to give us a positive number. The only one that's going to work, you can plug these other ones in. So if you plug in minus 1.66, minus 2.38, or minus 0.76 into here, you're going to get a negative number. The only one that gives you a spontaneous positive number is copper. So that's the correct answer. And we know that because it has the higher standard reduction potential. Okay, so this one says, what is the standard cell potential for the following reaction? We have 2 chromium solid plus 3 lead 2 plus gives 2 chromium 3 plus 3 lead solid. So we have to write out the standard reduction potentials for both. So in this case, our anode and our cathode so for our anode, this is going to be chromium gives chromium 3 plus 3 electrons. And our anode is going to be lead 2 plus 2 electrons gives lead. So if we look up the standard reduction potentials for the chromium 3 plus and lead 2 plus, E cell is going to equal minus 0.13 volts, which is the lead. And then we're going to look up the chromium 3 plus and take it as it is from the standard reduction potential table. And you're going to find that that's minus 0.74 volts. So the E cell in this case is going to equal positive 0.61 volts. Okay, so let's look at the next set of questions. All right, so we've got one where we have to do a balance. So this says balance the following reaction in acidic conditions. So what we're going to do is we're going to write the half reactions first, and then we're going to kind of follow through on the process. So let's look and find what's being oxidized and what's being reduced. So we have chromium Cr2O7 2 minus. So this is going to give us 14 negatives. So this is minus 14 here. We have a negative 2 overall charge. So that means that we have to have an overall charge of plus 12 divided by 2 is going to equal plus 6. So our chromiums are chromium plus 6. And then over here, our chromium is plus 3. So for the chromium species, this is being reduced. And let's look at the nitrogen, because I think that's the species that's going to be oxidized. So here we have minus 4 for the oxygens. We have a plus 1. So that's going to give us a plus 3 for the nitrogen. And then over here we have minus 6 with an overall minus 1 charge. So this is going to be plus 5. So yes, the nitrogen is being oxidized. Okay, so let's write down our half reactions. So we have Cr2O7 2 minus goes to Cr3 plus, chromium 3 plus. And we have HNO2 goes to NO3 minus. So now the first step that we're going to do is we're going to make sure that we balance the atoms other than H and O. So here we're going to have to put a 2, and here we're going to have to do nothing because all of our atoms we have 1 and 1 nitrogen. So now let's just focus on the chromium part. So with the chromium, we have to balance the number of oxygens. So we're going to put on the other side 7H2O, which means that we're going to get 14 H plus on that side. And the 14 H plus is to balance out the hydrogens from the H2O that we added. Now let's do the same for the reaction on the right. So on the right, we have the nitrogens already balanced, and we have a difference of 1 oxygen on the left. So we're going to add to this 1 H2O over here, because we have 3 oxygens on the right and only 2 oxygens on the left, so we have to add an oxygen. Now we have a grand total of 1, 2, 3 H plus to add to the other side. That's because we have 3 hydrogens on the left. Now we have 3 hydrogens on the right. So now we have to do on both sides our electrons. So on the left, we have a grand total of, so let's look at the chromium half reaction now. So we have to do electrons. So for the chromium, we have a grand total of positive 12 on the left and positive 3 on the, and positive 6 on the right. So if you add this up, we have 14 pluses and 2 minuses gives plus 12. We have 2 times 3 plus is plus 6. So that means that we have to add 6 electrons over here on the left side of this reaction. And for this guy, we have to add a total of 2 electrons on this side to balance out, because we have 3 pluses and 1 minus. So we need another 2 minuses to get it to be 0, like on the left. So now the last step is we have to multiply this by 3 in order to get the electrons to balance, because we have 2 electrons here and 6 electrons here. So this is going to give us 3H2O plus 3HNO2 gives 3NO2 minus plus 9H plus 6 electrons. So now our electrons are balanced. So let's combine these two into our overall. Then we'll cancel. So we get 6 electrons plus 14H plus Cr2O7 2 minus. And then we're going to start adding reactants from the other, plus 3H2O plus 3HNO2. And then over here, we're going to have our products. 2Cr3 plus 7H2O plus 3NO2 minus plus 9H plus 6 electrons. So now we can start canceling. So the electrons are the first thing to go. We have 9H plus on this side. Those are going to go because we have 14H plus over here. So we're left with 5H plus. Cr2O7 doesn't cancel. And then H2Os, we've got 3 on this side and 7 on this side. That's going to leave us with 4 H2O on the right. So we're going to get 5H plus over here, which is going to get an aqueous, plus Cr2O7 2 minus, which is going to get an aqueous, plus 3HNO2, which is going to get an aqueous, is going to give 2Cr3 plus, which is going to get an aqueous, plus 4H2O, which gets a liquid, plus 3NO2 minus, NO3 minus, which gets an aqueous. Okay, so that should be balanced, and you can check the balance if you want to make sure. Sorry, I wrote this as NO2. It should have been NO3. I just carried it down wrong. So that was 3 NO3 minus and 3 NO3 minus in this line, here and here. Okay, so now for the last one, it says, what is the equilibrium constant for the following reaction at 400 Kelvin for this reaction? So it gives 3 carbon plus 4 H2 gives C3H8. Then it gives us some thermodynamic data. Delta H is equal to minus 104.7 kilojoules. Delta S is equal to minus 287.4 joules per Kelvin. So we have to recognize that this is going to be we're going to need 2 different equations for this. So the equilibrium constant, delta G, is equal to minus RT ln K. Now notice that I'm not putting in delta G naught because we're at 400 Kelvin. So what we need to get in this case is we need to get the delta G for this reaction not at standard conditions, which is going to equal delta H minus T delta S. So we're going to use the delta H and delta S at this temperature to get the delta G. So let's start with that. So the delta G in this case, we're going to take our kilojoules, and remember, you have to pick a set of units for this because we have joules and we have kilojoules. So I'm going to go in joules because over here, this has to be in joules over here for this to work. So we're going to pick joules. So I'm going to do a quick conversion of my kilojoules to joules. So this is going to be minus 104.7 times 10 to the third joules for my delta H. And then we're going to subtract the temperature, 400 Kelvin, times delta S, which is minus 287.4 joules per Kelvin. So delta G, if you work that out, is equal to 10,260 joules, which is going to be a positive. And then if you plug that into the delta G expression, you get 10,260 joules is going to equal minus 8.314 joules per mole Kelvin times 400 Kelvin times the natural log of K. So if you solve for K, what you're going to get is 4.57 times 10 to the minus 2. So hopefully these problems give you a sense of a review of some of what might be on the exam, what might be on the upcoming exam. Now there are so many different types of questions in this case that we can't review them all. Meaning there are just so many equations in chapter 19, so many equations in chapter 18, and so many equations in chapter, well, not so many equations in chapter 20, but there's a lot of reactions in chapter 20 that you have to memorize for the radioactive decay. So a lot of this is going to be just looking through and making sure you understand how to do everything. But this gives you a sense of some of the questions you might get.